Okay. So if you have a unramified extension of the p-adic numbers, p-adic integers, and you have a finite group. Then the group algebra breaks up into blocks. Okay. Some blocks. And some people are interested in this derived category of one of these blocks. And this lecture, it's about a, another, so that this derived category is some kind of triangulated category. And this lecture is about another triangulated category. All right. Triangulated like that for short, attached to this block. And in some sense, it's a deformation of this guy. In some sense, it's a smooth deformation of it. Okay. This is my first time giving a talk on an iPad. So excuse me. All right, so I just want to say at the beginning what kind of thing this triangulated category is, and how it's maybe related to the usual derived category of the group algebra. So a typical object of derived category of the group algebra is the permutation module, a permutation module. Okay. So if you have a finite set with an action of the finite group, you can look at the free module spanned by that finite set, and that has an action of the group. And this has a matching object in this other triangulated category. I'll call it KUX for now. I don't know where to put the O. There's this O involved, which a little O here. That's this guy up here. All right, so there's at least in this other world, there's such a thing as a permutation module. And I can tell you what the homomorphisms between two permutation modules are. So, well, it's maybe this is a triangulated category, so we can shift by some number. And this is going to be a 0 if that number is odd. And it's going to be the, let's see, formal O linear combinations of vector bundles, of complex vector bundles on X times Y divided by some equivalence relation. That's if N is even. If N is even. And this equivalence relation, so these are virtual vector bundles. But where you take formal linear combinations of vector bundles, but maybe the things that you scale them by can be p-adic integers. And this equivalence relation says that, well, a vector bundle is equivalent to 0 if the trace of an element of a finite group on a stalk of that vector bundle is 0 whenever whenever gx is equal to x and gy is equal to y, and G has p power order. Okay, so that's
is it equivariant vector bundles or
equivariant vector bundles? I'm sorry. Of G equivariant.
But XM are just finite sets, is that correct?
Yeah, just finite sets. So this isn't this is a definition of some additive category. Maybe it's even a kind of famous additive category. And you can imagine how to compose these vector bundles. You can convolve vector bundles in about the same way that you can multiply matrices. Okay, and this additive category is going to be a full subcategory of some larger triangulated category, which is some analog of the derived category of the group algebra. Okay, so let me back up. So backing up. Okay, so in modular representation theory, can I write MRT? Modular representation theory, you have groups and algebras, and they act on, they usually act on like a little k vector space, little O module. And my storytelling will go smoother if I round these off to just FP and ZP, prime field and p-adic integers. So that's K and that's O. And representations, they make a category. And maybe I can write that sentence down. Okay, representations make a category. And if your representation theory is not semisimple, okay, not semisimple, it can pay to look at complexes of representations. I don't know. So each chain group in your chain complex is a representation. The homology of this chain complex, the ith homology group, is a representation. Okay, and these complexes are the objects of a triangulated category. Such as the derived category. And some questions of modular representation theory are questions about this triangulated category. Okay. Okay. So so long ago, I mean, algebraic topologists for a long time have been encountering triangulated categories of a different nature. The objects are not complexes of anything. So for example, there's the category, maybe in color. There's the category of spectra. Spectra are the objects of a triangulated category. And some of these triangulated categories, they could appeal, maybe they have appealed to a modular representation theorist. They're appealing in a MRT-like way, modular representation theory-like way. So for example, G spectra. Okay, but there's maybe a daunting aspect of studying representations on spectra. Maybe more about spectra in a second, but there's some daunting aspect of it, which is that spectra are very complicated. Okay, and the category of spectra is very complicated. There's a but in front of this. So we know all the FP vector spaces. We know all the ZP modules. And we even know all the complexes of them up to quasi-isomorphism. But we don't and we can't know all the spectra. That's kind of too tall of an order. So maybe it's premature to bring representations into it. Okay. Before trying to say what this talk is about, let me just give here just as little as possible about spectra. Okay, so I just have two things to say that maybe would help somebody orient themselves if they didn't already know a lot about spectra. So one of them is that every object of this category of spectra, it is, or maybe represents, a cohomology theory, an extraordinary cohomology theory on ordinary topological spaces. And maybe there are some famous axioms for an extraordinary cohomology theory. They're 70 years old. Maybe it's, and you can guess looking at that definition, if you know it, what a morphism between cohomology theories is. And it's much harder to quickly tell what is a morphism. Harder to quickly tell. Okay, but a map and a homotopy class of maps will induce a map between cohomology theories at least. And then the other thing to say is that where chain complexes have homology groups, have homology, so HI of C, spectra have homotopy groups. So pi I of E. Maybe I'll leave it there. So this lecture, I just want to make a suggestion, which is to look for ring spectra. More or less ring objects in the category of spectra, so that the triangulated category, let's call these R, of R module spectra is, well, it's not too complicated. Okay, then study G actions on those. So in the 1900s, changing rings to ring spectra and modules to module spectra was called brave new algebra. by, oh, good Willie, somebody famous.
Waldhausen.
Waldhausen, I'm sorry. Okay, so here's an example of how that could work. So there are ring spectra called, maybe they're called HFP, HZP, such that the category of HFP module spectra and homotopy classes of maps between them is equivalent to the usual derived category of vector spaces over FP. And then suitably defined G actions on these, G actions on HFP module spectra and homotopy classes of maps between them. That's the usual derived category of modules over the group algebra. And the same for with FP replaced by ZP. Okay, and similarly for FP replaced with ZP. Okay, so I said that spectra are extraordinary cohomology theories. So if spectra are extraordinary cohomology theories, then HFP is its ordinary cohomology. It represents ordinary cohomology. Ordinary cohomology with FP coefficients. So this is some ring spectrum, some spectrum at least, whose it has a homotopy group in degree 0, and every other homotopy group has every other homotopy group vanishes. It's Eilenberg-McLean spectrum. And HFP, HZP, other Eilenberg-McLean spectra, they're not the only spectra whose category of modules is easy to understand. So, so it is also easy to understand, at least the triangulated category of what I'll call, maybe I should, of some other spectra, other ring spectra. So for instance, the ring spectrum called KU. This represents topological K theory in the sense of, or complex topological K theory in the sense of Tia and Herzebruck. It has homotopy groups. Its homotopy groups are Z in even degrees and 0 in odd degrees. And it's a ring spectrum. Has the structure of a ring spectrum, can be given the structure of a ring spectrum. So in particular, its homotopy groups, maybe they're actually a graded ring. And that graded ring is this Laurent polynomial ring. B is a famous element in pi2 of KU. Okay, and basically, well, the modules for KU are easy to understand, or at least easy to classify. So the category of KU modules spectra, and homotopy classes of maps between them. Well, between them. It's equivalent to some two periodic version of the derived category of abelian groups. So if you have some abelian group or derived category of abelian groups, like some object in the derived category of abelian groups, and maybe the usual, I don't know, z plus z mod 3 plus a shift of z. This matches a KU module spectrum, which is easy to guess what it is. It's you'd call it like KU direct sum KU mod 3 direct sum the suspension of KU. So KU modules are determined by their up to homotopy equivalence. They're determined by these two abelian groups, pi 0 of M and pi 1 of M. KU module M. Okay, and if you looked just at the, so I don't know how to say two periodic version of the derived category very fast. If you looked just at objects with no odd homotopy groups, let's put it that way. So the full subcategory spanned by just M with pi odd of M equal to 0. That just is, its homotopy category is the usual category of abelian groups. Not complexes or anything like that. Okay. Okay, so the proposal is to study group actions on these.
Is this result of Pausfield that you're using this equivalence, or is it easier than that?
Does it take anything that complicated? I'm afraid I don't know what.
Okay.
It's you. Well, it helps that okay, it helps that this ring pi 0, that the integers are it's a one-dimensional ring, and it helps that KU has a lot of vanishing homotopy groups. Okay, so just a definition. Okay, this can be a definition too. Let's write, hold on. Okay, but the left-hand side of this, okay, this has more structure. It has kind of infinity categorical structure. So the maps from one module to another, it's the space of connected components it's the set of connected components of some space of maps from M to N. And each component of this space of maps is some relative of the stable unitary group or the stable Grassmannian. So I'd like to write, and that's a much more complicated, richer thing than the derived category of abelian groups. Well, let's say it's a different thing. Let's not make a value judgment. It's just a different thing than the derived category of abelian groups or any what would usually be meant by an infinity categorical version of the derived category of abelian groups. And let's write that. Let's write mod KU for the infinity category of KU modules. And now here's a definition. A representation of G on a KU module is a functor from the classifying space of G to this infinity category. And then a comforting proposition is that, that there's an associative ring spectrum that plays the role of the group algebra. Let's call that KUG. Such that this category of functors is equivalent to, let's call them left modules over this group algebra. All right. So let's study this category. And compare and contrast it with the derived category of the group algebra of G, or, and soon, with the derived category of the group algebra with p-adic integer coefficients. And the claim is that the structures that you'll see, that they'll have lots in common with normal modular representation theory, and that, okay, with normal representation theory, modular representation theory, and that some computations, certainly not all, are easier than a normal modular representation theory. So a relevant precedent for that is this result of Atiyah from 1960 or so. So the cohomology of a finite group with integer coefficients, it's very complicated. It's a complicated ring with lots of torsion, lots of nilpotent elements. And the K-theory of this classifying space, well, it's completion. Well, it's 0 in odd degrees. And it's a completion of the complex representation ring of G at the augmentation ideal. Well, in particular, it's torsion-free, reduced, vanishes in a lot of degrees. And okay, if you complete this at a prime, structure is even a little simpler or more explicit. So here are some ring theoretic aspects before going on, aspects of KU. So one of them is that you can complete KU at a prime. You get something called, I'll call it KUP. And modules over KUP, they're maybe they're about the same, are related to the homotopy category of them is the two periodic version of the derived category of modules over ZP. You can also reduce KU mod P. You get something, let's call it KU mod P. But there's something uncomfortable about it. So it's not commutative. It's a ring spectrum, but it's not commutative as a ring spectrum. I don't know actually how important that is, but it means I won't talk about KU mod P. And then also you can adjoin nth roots of 1 to KUP, so long as n is prime to P. But you can't adjoin pth roots of 1 to KUP, or 4th roots of 1 to KU2. Okay. Okay, so let's see, let's stick to KUPG and try to compare it to the group algebra with p-adic integer coefficients. So here's a notation. All right. Left modules over this group algebra. I'll put a little superscript FT here, finite type here, for the modules, KUPG modules, whose homotopy groups are finitely generated over ZP. Try to compare this to the usual bounded derived category. Of the group algebra of G. And I have 5 minutes, then I'll stop. So one of them is that if you have a projective, calling it P bar, if you have a projective ZPG module, then there's a unique object in here, P without the bar, with pi 0 of P equal to P bar and pi 1 of P equal to 0. So there's some piece of this category that's familiar, resembles the category of, it is the category at the level of homotopy classes of maps. It is the category of projective modules. Okay, and then maybe furthermore, it's easy to compute from a projective module into some other module, even in the KU world. This is equal to Ham in the ZP world between P bar and pi 0 of n. Okay, And along those lines, maybe because of that, this ring, it has the same blocks as the usual group algebra. And the category of these finite type modules, it's going to break up in the same way. Be a product of it'll be a direct product of categories in the same way that the derived category of the group algebra is a direct product of triangulated categories. Okay. Maybe some differences.
Could you say that? Why is that again? Just you can actually take a little bit longer. We saw the other times.
Because let's see, with some hesitation, I'll say it's because idempotents are pretty nice to work with in I can't answer your question. I'm sorry.
Isn't the endomorphism ring of the group algebra the same on both sides?
Yes, the endomorphisms of the free module are the same on both sides at the level of homotopy classes. Yeah.
Right, and then you lift those idempotents and you.
Yeah. Okay. And then some differences. Here's one difference. So if G is a commutative P group, and we'll call it G sharp, is the Pontryagin dual commutative P group, there is a natural equivalence of infinity categories between the finite type modules for G, this has only one block, and the finite type modules for the Pontryagin dual. So it's, I mean, of course, G and G sharp are actually isomorphic as groups, but this equivalence isn't induced by an isomorphism like that. Like it sends the trivial module to the free module, exchanges the trivial and the free modules. So that this is so an equivalence between categories of algebras is induced by some bimodule. So this is induced by an action of G times G sharp on KU or KUP, which is in turn induced by an action. Well, I haven't really even mentioned that KU is related to the category of complex vector spaces, and G times G sharp, it acts on the category of complex vector spaces so there will be some cocycle describing that action, which lives in H2 of G times G sharp C star. And that bimodule induces an equivalence. If you put these finite type superscripts. And well, this is 40 minutes. Shall I stop? I have one more thing to say.
No, I mean, I think Jordi made an executive decision just before the first talk, which was that we could go a little bit longer. So the other talks have actually gone like 60 minutes. So you should just go on, and when you're finished, we'll
Okay,
start asking questions.
it'll take 41 minutes instead of 40 minutes. So,
No worries.
I said, so maybe this counts as a difference. So in what sense is KUPG a deformation of ZPG? Let me give kind of two answers. So one of them is just in the sense that KUP is a deformation of ZP, or of maybe of HZP. So there is a another ring spectrum called connective K theory, traditionally written in lowercase letters. It's called KUP. Okay, with the homotopy groups of, if the homotopy groups of capital KUP is some kind of Laurent series ring, Laurent polynomial ring, then the homotopy groups of little KUP, that's just a polynomial ring. And if you set B equal to 0, you get HZP. And if you invert B, you get KUP. I don't know if it's even necessary to put these operations in quotes, but I will. You get KUP. Okay, so that's one sense. And maybe completely the same sense is that every morphism space in this category, just in this additive category, the homotopy category, every Hom from M to N has a filtration. This is in the KU world, this Adams filtration. And the graded pieces of that filtration, there are the target of some spectral sequence. So the graded pieces show up in X in the usual, this maybe is KUG and this is XZPG. The usual kind of, the usual kind of X group between usual kinds of modules. Okay, so that's a little story about it being a deformation. And then why is this deformation smooth? Well, I think for a associative algebra, you call it smooth if the diagonal bimodule. So we would call CPG smooth if the diagonal bimodule had a finite resolution as a G times G module, or if it were compact in the derived category of all ZPG modules. And it's not. But well, there's something nicer about this guy. So KUPG, this is the theorem of Greenlee, Sadovsky, Hopkins, Lurie, I think. Well, it's not is compact, not quite in the category of all, not necessarily finite type G times G modules, but in this p-adic completion. of this category, which I okay, which I'm not prepared to talk about, I guess. I'll stop.
Thanks. So we have plenty of time for questions.
Hi, David. I have a question.
Hi, Ben.
So these, I mean, I know more about normal cohomology, where there are these nice cohomology operations. So on KU, the Z version, is there an action of like differential operators on ZQQ inverse, which lifts to the action of spaces or spectra?
Oh, sorry, an action of what kind of differential operators?
Or for little KU, maybe it's easier, but differential operators on the ring ZBB inverse. Are there cohomological operations or whatever the appropriate notion is that?
There are operations. Let's see, if you complete it, if you completed a prime, there are the so-called Adams operations. I don't know if these are automorphisms of the ring as a
vector space.
As a ring, yeah, as a
ring. I see. Right.
As a ring, is that the right thing to say?
Are there derivations?
And they act in different ways on different homotopy groups. And I don't know. That's the only thing I can think to say.
Cool.
Yeah. So I mean, you have this algebra operations, which certainly acts, right? So it's the self maps from KU to itself. So that's some algebra, just like if you did ordinary cohomology, you would have the Steenrod algebra acting, and you have this analogous thing for KU.
And what is it? Does it have? Is it that big? Does it have enough stuff?
Yeah. So it's generated by these Adams operations.
Can I ask Dave,
Yes.
what would be a first case to look at? Like, we love Boy's conjecture and things like that. And have you thought about a first potential case where you could...
Yeah. So for some groups, you can maybe for, I don't know, cyclic defect or something, you can find a bimodule which is represented by a two-term complex, right? So you want to get from ZPG to ZPH, connect some blocks between these guys, and you can find so that there's sometimes a functor from here to here. It's represented from the derived category of here to the derived category of here, and it's represented by a two-term complex, which has the form of like G times H modules. And it has the form, there's one module in degree 0, and then there's one module in degree 1, and module in degree 1 is projective. I think I'm saying this right. So here would be some bimodule or complex of bimodules which induces this equivalence, and at least exists. You can write down the same object, or the well, you can try. Sorry, so long as you could find a version of this M0, you could you would have a version of this, is that always simple? I'm not sure. You would have, sorry, so instead of, so Ham from this P1 exists, and maybe this M0 exists, and then Ham from P1 to M0 is the same in both worlds, in both the K-theory world and the usual world. So you can pick out the usual object, and then instead of talking about the two-term complex, you can talk about the mapping cone of that map, and then this would be a good would be a bimodule over KUP G times H. Did I skip an important sentence? I don't.
What do you get out of it that you don't get in the normal setting?
You wouldn't get anything out of it. I mean, like you would get you would get a parallel statement to a normal setting theorem. Yeah. So a really good question is whether there are, like, if you could prove that two blocks in the K-theory world were equivalent, could you conclude that the two usual blocks were equivalent, or vice versa? And I guess I don't know. One thing to say is that there are more automorphisms. There can be more automorphisms in the K-theory world of a category, I mean, than in like this one here. There can be more automorphisms of a category. If you picked an isomorphism between G and G sharp, then this would be some kind of exotic equivalence of the category of representations, which doesn't exist in the usual world. So that's, I know, some indication that there's more equivalences to play with, but I don't know if there really are or not.
So, but in your original theorem, there was an assumption that the group was abelian, right? So that was how you got your, you have
yeah.
The
Well,
abelian group and its Pontryagin dual.
Yeah. Now that can be.
Can you say something about?
Oh, how you about this theorem?
Yeah, and the assumption that it's that
Oh,
the
is
group
there?
is abelian.
I just don't. Is there such a thing as the point? If there's a dual group.
No, right.
Yeah.
I'm asking
Well,
what should be the right hand side in the case where the group is not abelian?
Yeah, I have no idea.
So can I ask a question? So the usual, say, Deraf category, the center of that category is, I don't know, the center of the group algebra, or maybe you get the Hochschild cohomology. So in the KUP setting, what do you get?
Yeah, it's another. You would get this. Maybe Lustig wrote this ring down in the 80s that you can look at G equivariant vector bundles.
Okay, the Drinfeld, something having to do with the Drinfeld double of the group algebra, you mean? Or?
Oh, is that what that is?
I don't know.
It's conjugation equivariant vector bundles on the group divided by this equivalence relation. So the spectrum of that ring is interesting. The spectrum of that ring well, okay. This is close to being true. The spectrum of this Hochschild cohomology ring, this ring of conjugation equivariant vector bundles on the group, but divided by this equivalence relation. This equivalence relation would pick out a block of that bigger category of equivariant all equivariant vector bundles. the principal block. So the spectrum of that principal block, it's one-dimensional, so it has closed points and open points. And the closed points are in correspondence with blocks of the group, and the open points are in correspondence with cyclic groups of p-power order. So in particular, there's the specialization map, which I think is the Brouwer, one of some version of the Brouwer map from, I'm sorry, I haven't thought about this in a while.
Yes, no, I see what you mean. Yes, I see what you mean. Yes. Okay, thanks. Yeah, so that's something a little bit richer than once you're linearized, once you're at the ZRF category.
So I had a question about, so in the classical case, one way we produce representations take like the linguistic variety, take cohomology, and in this setting, I guess you take the K theory of the linguistic varieties, you get an object in this category, right?
Yeah, you have to watch out for the difference between complex and algebraic K theory. Right, so I know GLNFP acts on some kind of linguistic variety, and or maybe times a torus acts on some linguistic variety, and okay, so it therefore acts on, and this is some variety over FP, right? This is some variety over FP, or maybe over FP bar. So since this group acts on this variety, it's going to act on well, the category of coherent sheaves on this variety, and therefore on the algebraic K theory of this variety. And this is not a KU module, not a KU module.
This would be related to motivic cohomology anyways. You don't want motivic cohomology, you want
yeah, you want
LSE cohomology. Yeah, exactly.
I think what you'd want is the topological K theory of the étale homotopy type of that variety.
Mm-hmm.
And you can get that. There's this Thomason theorem that lets you get that out of here, which is by applying a functor called LK1. So LK1 of this is a module for LK1 of the algebraic K theory of FP bar. And K1, there's a prime. K1 is actually short for like K1 comma L. And this is KUL. I think that's Thomason's theorem. So yes, you can get this delinguistic bimodule in this world also, as long as maybe it's not surprising in non-defining characteristic.
Right, but I guess yeah. Does the story continue? Like I can ask about characters, or I don't know, like. I don't know. To what extent does the kind of classical theory extend to the situation?
I have no idea. I don't know how to do. I mean, I don't know much delinguistic theory. So what would you? I know enough that you say that you can define this bimodule, and that's then I run out of gas.
Mm-hmm. Yeah, I guess for characters, like there's a class in the Hochschild cohomology that would correspond to a character, or maybe like in particular cases, these objects provide the equivalences for Brouwer's theorem, I guess.
What kind of objects?
Oh, like specific delinguistic representations.
Yeah, so you, I guess, maybe, I don't know what the state of the art. So I read an essay or something a long time ago. Said that they were having, let's see, were people at one time having trouble proving that these delinguistic varieties gave Brouwer's equivalences? They look like maybe they do, and I don't know if maybe there was some trouble. So I don't know if it's if that's an accurate dredged up memory of something that didn't work in the usual world. I mean, maybe it's worth trying in the K-theory world, but I'm not even sure
Yeah, what's difficult is that Lustig's work suggests that one should be looking for geometrical things, and so it's difficult to know where where is Boy's conjecture holding. There are some geometric things that should explain it, but you should invert certain things, you should linearize, you should maybe complete. You have to do something before you get your you get some sort of equivalence, and it's I think one of the issues is there. So this is an intermediate that the world, David, you're describing is interesting because it's one of those worlds that are in between the geometry, where the delinguistic variety is not something invertible in any sense directly. So you need to do something. So before, and you can take cohomology, but you would want to keep a little more structure. So that's what's great with this construction, is that it does. So maybe it's a little bit too topological. I mean, a little bit too much has been inverted, but yeah, it's not clear yet, I suppose.
What would this be equivalence between, actually? So, because now you would already be working in the local world, right? So
you would relate the whatever the KUG modules to the KUNG of P modules, or you would want ideally something like that. And the problem at the level, at the geometrical level, is a problem. I mean, you have with topology already, is that you have to do some difficulties with dualizing in some sense. You have an object, tensors the dual, should be something. But dualizing is an operation that's going to it's difficult for spaces. I mean, you typically you have to go to spaces up to homotopy or something like that to have good duals. So there's this difficulty in Boy's conjecture dualizing. So once you are at this KU thing, that's good. You can dualize. So you can probably. I think you should. I mean, what David explained is the kind of objects that would give version of Boy's conjecture in general at this KU level. You would expect that the delinguistic variety is going to do that. Yeah, I would think so. So one thing that one should look is what is the Hacker algebra in this setting? I don't know. You would get a space instead of a Hacker algebra showing up. So that might be the first thing one should compute.
But yeah, I guess you could ask about the homotopy groups of that Heck algebra. That would be a kind of classical ring, right?
And you would expect this to come from an interesting, say maybe finite dimensional space.
You also, didn't you? I saw you also have some sort of statement for non-abelian groups where you have things parameterized, or maybe a conjecture where you get a formula for your representation ring in terms of centralizers of these elements of order prime to P.
Yeah,
correct.
You're talking about the Hochschild this center of the category again, or
yeah, or not the center of the category, but your your category of KUG modules or compact objects in that category or something like that. Maybe we can also stop the recording and then we can chat.
I was going to say, by the way, this superscript FT. Did I write some superscript FT?
Yeah.
Somewhere I did. Those aren't the compact objects of the category. There's some like maybe they would become the compact objects. I'm actually not even sure if that's true. Maybe they're the compact objects after you p-adically complete the category of all modules. But not before then, I don't think. So like the trivial module, it's still not exactly compact because there's some ugly difference between k-homology and k-cohomology of because k-homology of BG is not exactly the same thing as k-homology of BG, or I mean, it even looks quite different. But so this to talk about, even to define some of these functors, I think it does require this Hopkins-Lurie thing.
I see, right, yeah. So, well, that's good. Then you're inputting something. So, you might get something out also. Any more questions? Otherwise, we can thank David again, and then we'll reconvene in 24 minutes. But then we can keep chatting here for once we're done.
Thank you. How do I surrender the screen? Do I have to?
Just click stop sharing. It's on top somewhere.
Yeah, okay.
Very quick question. Is there a spectrum? So you talked about there's a spectrum that's like the derived category of abelian groups or vector spaces.
Yeah.
Is there a spectrum that's like the not the derived category, but the other triangulated category, like P complexes of vector spaces?
Oh, I don't like this P complex, like this. Like you would take the homotopy category of P permutation modules. I think that's a popular one. Is that the one you mean, or
I just mean like g to the p equals 0. Usually in characteristic P.
Oh no! Oh, I have no idea. Oh, I don't know how to.
And there's the notion of homotopy.
I don't know what that is as a spectrum. There are these. Is that what a matrix factorization is? Is it?
No, that's not. A matrix factorization is more like two periodic things.
Okay.
This is more like a different kind of homological algebra. It's a stable category over a Hopf algebra.
Yeah, I don't know.
So do you know any examples of, I mean, are you envisioning this as like an extension of modular representation theory, or do you know any examples of like a way that it kind of wraps around and like applies to something classical?
No, I have no applications. I mean, it would be interesting to do this for a p-adic group instead of a finite group. But also that was one thing on my mind, and then you could maybe define some rings that act on the K theory of a locally symmetric space. That was something that was once on my mind, but I have nothing really to say about it.
I actually lost internet for the past minute, so I don't know what you said, but
I think maybe you and I have talked about it before. That
okay, it's the stuff we talked about before.
To study maybe the K theory of a arithmetic symmetric space, locally symmetric space, and cut that up with some version of Hecke operators. So it would be interesting to do this instead of for a finite group, for a p-adic group. That was one thing that I thought, but I don't have any No, nothing has wrapped around and
but you mentioned that you had thought about the Heck algebra in that context, right? Like, have you thought about the Heck algebra for?
yeah, yeah. But like the there's something enticing about doing Smith theory, like you, that the K theory. I don't exactly know in what sense it's true, but just the mod P cohomology of a space is sort of related to the mod P cohomology of the fixed points, and it sort of feels like the K theory of a space is related to the rational cohomology of the fixed points. But that's also something that I haven't really made hay out of.
Of a P group or
Of a cyclic group, I guess.
you're taking, right.
The K theory of a space. Well, so there's this, here's some Hecke algebras up here, actually. Oh, I'm no longer sharing my screen. Can I bring that back? It's too late, probably.
If Jordy lets you.
It shouldn't be too late. You should still be co-host. Yeah, you still are. You still can, yeah.
There was, this is a Hecke algebra, isn't it? This is the endomorphism ring of a permutation module. Would be some kind of Hecke algebra. There is a homomorphism from this Hecke algebra to the usual Hecke algebra of the fixed points. So maybe there's some localization of the whole category of modules, which looks like the category of representations on a rational vector space. Where you just, yeah, this definition, this condition here is cooked up so that you can just take, the trace at G, trace of G on some morphism in this space is, it defines a map to from maybe I'll just write rational number, maybe I should write complex numbers. The permutation module over C spanned by the fixed points, as long as G is of P power order. So this is a, so in another context, this would be called the Brouwer homomorphism. But instead of going from like two of the same kind of things, it goes from K theory to rational cohomology. I'm babbling a little bit, sorry, but okay.
This is this business that you've told me several times that kind of Smith theory decreases chromatic height by 1.
Yeah, maybe it does. That's the Markovi or somebody's blue shift. There's something called the blue shift. Yeah.
So it decreases what?
Decreases something called the chromatic level.
Okay.
So just a finite field has chromatic level infinity, and the rational numbers has chromatic level 0, and K theory has chromatic level 1, and then there's a lot of steps to go in between. But when you there's this, yeah, it seems like Smith theory, it brings you down 1 chromatic level.
Yeah, but if you're infinity, you don't.
Yeah, and then you, yeah. So one of
that's
the
why regular Smith theory holds.
Yeah. Okay. Yeah.
I mean, you can see that at the level of characters. I mean, if you think of elliptic cohomology for the group, I mean, you get some kind of double class functions of 2 commuting elements. And the Smith theory, you would fix one of the elements to be a P element, and then you would have a function of the centralizer, which becomes a class function, which is now level 1. So you start with your elliptic group law, and you go down to level 2 to K theory level 1. So I suppose that's part also of what you have in mind, David.
Yeah. So there are a lot of recent theorems about this blue shift where they've actually like proved these kind of conjectures that it, that it can, you can ask how much can it drop by, and the fact that it can only drop by by 1. Yeah, that's
How much can it drop by when you do what?
well, when you take fixed points, or
Oh, okay.
how much can if you take homotopy fixed point, how much can the the chromatic height drop by? So you can go down 1, but the question is how much further can you go down? So if you take it under a cyclic P group, and there's a whole story there. How much for more complicated groups. I guess maybe it's not. I mean, this is for cyclic groups. Yes.
Can you give me a keyword for that? Like you have some.
Well, I mean, this is recent papers about the what's called the Balmer spectrum of the equivariant stable homotopy categories.
ALMER. The what spectrum?
Paul Balmer from UCLA. Balmer, BALMER. Balmer. So,
well, that's the author of a paper or the name of a spectrum.
Well, the Balmer spectrum is a spectrum, and then Paul Balmer is a person who has also written papers on this. So if you Google Balmer, then you'll find some hits, and that will show you in the right direction. Yeah. So. Yeah, but it's a great question. The Smith theory, it turns out all over the place, and it's key to all sorts of stuff.
David, I was really interested by by your comment about the connective K theory and how you can view this as kind of a family with, when you invert B, you get KU, and when we set B to 0, we get HFP. And sometimes, I mean, like often we prove things by constructing something and then checking that it localizes correctly. Like in localization theorems in equivariant cohomology or something, you check something at the generic point.
Right.
And I was just wondering if there's like if that has been done in that setting.
What's a good example of that method that you're?
I was kind of dreaming that you could let's say construct some equivalence, which like construct some functor which is defined over connective K theory, and then invert B and see that it's an equivalence. And deduce that that's an equivalence for HFP.
Yeah, I don't know. What?
Can you localize away from that? I mean, you said you think of things as that. So Jordi's question, that would require you to to be able to localize in a different, go in a different direction from your KU modules, KUP modules, from which you could not go back to representations of the group. So is there something like a generic point in your deformation? Or?
I don't know how literally to take it. Like if there's a parameter in this deformation, then it's this bot element, it's B. And And I don't think there's any, you can't set b equal to some other value besides 0. You can invert it or set it to 0. I don't know what else.
No, but that's good. That's
Okay.
good. That's like I don't know, discrete value, a circle. I mean, a small disk. You can either go to the the point of your disk or just remove the point from that small disk. So what happens when you do the bot element to 0?
There's a map from connective K theory to the usual Eilenberg-McLean spectrum, which carries the bot element to 0 and every power of it to 0. So if it's fair to say that that's the same as, right? I mean, in algebraic topology, I don't know to what extent you can really talk about dividing by an ideal. That's like a sensitive thing. But there's, I don't know, it seems like you're setting b equal to 0 and you get the Eilenberg-McLean spectrum. That's there is some, like Atiyah's early career was about proving things that maybe some of them were things that atoms had proved in complicated ways using cohomology, proved it in a simple way using K theory. I don't know, like the Hopf invariant 1 problem is a example of that. I don't know. That's just another thought along these same lines.
But in this case, you can kill B, right? Because it's a regular element, so you can just.
Is that a technical term?
You can. Yeah. I think so.
You can kill regular elements.
Yeah. I think that's by some Lane-Weber exactness or something. We have some other stable homotopy series down the line who can tell what the exact conditions are.
The one thing that always confuses me in the stable homotopy theory is like there's these various notions of G equivariance, like genuine as well. Does that have any significance for your story?
I think I'm not positive, but I think maybe I'm not positive. I think maybe if you complete the genuine category at a prime, so in the genuine category, there's you can talk about K theory still. There's some, they call that global K theory or something like that. So there's some genuine version of K theory and modules over K theory. So you can do that, and maybe it ought to be richer. But I think if you complete it at a prime, then that category breaks up into little pieces, little blocks, which are the same as the non-genuine, the more Borel version of. Now, I don't know if that's actually true. I just suspect it's true that this genuine category, if there's after you talk about KU modules in it and complete it at a prime, that you'll just get it's a bigger category, but it's bigger because it's a product of categories that are related to like centralizers in the to these more naive is a technical word. I mean, these Borel, I was talking about the Borel version. And I think that just at the level of, if you're just looking for triangulated categories that resemble representations, then that's as rich as anything you'll see in the genuine world.
But sometimes the difference lies exactly in there's a completion theorem. That would usually be the case, right? But maybe there's not here because you're only looking at those which are already KU modules or something like that. Okay, but maybe if you're already also p-adic or something like that. So. You know, there's a lot of stuff there. Super.
Thank you, Jesper.
Yes, Daniel, you're taking over as chair here for the next talk. So you'll be in charge. You're muted. No.
Yeah. So the next talk will be in 4 minutes. So Nate, I guess you will have to either share your screen or a tablet. So Jordi, could you make him a co-host? I don't think I can.
Jordi went to get tea.
Yeah, probably.
We still have a little bit of time, I guess. Yeah, Nate, if I suddenly disappear, it's because like it's getting late here in Copenhagen. So if then I'll watch the end online.
I won't be offended.
Well, the problem is that when everybody wants to watch the video, and then nobody was at the audience.
No, it's always nice to watch it live. You know, it has a special feeling.
I'm joking, don't worry. Go to sleep. Actually, I was watching some of the video. I really want to ask the question and realized that was not alive.
Yeah, that's a problem. Yeah. But you can probably email the speaker. He'll probably be happy to answer. So.
Well, it's better to ask during the talk because that time you have a freedom of asking any question and the speaker has the obligation to answer it. After that, the speaker can ignore your email.
Right.
Great comment, thanks.
You don't have to feel offended, Raphael.
It's good to be reminded of that.